Welcome everybody to our last colloquium before the summer break. We're currently planning the program for afterwards, and we'll soon be sending announcements. We already have some exciting and nice talks planned. But now we're very happy that Stella kind of concludes the first session of the colloquium series. I myself have to excuse myself after I did this short introduction. Stella's recording the talk. We can, if she consents, again upload it to the webpage. And I wish everybody a lot of fun with this talk. And Stella, thanks again for doing this, and please go ahead.
Thank you very much for the invitation. It is truly my pleasure to conclude this year's colloquium, and I'm looking forward to next year's edition with many more speakers. So the idea for the talk that I had today was actually to introduce 3 very recent projects that I'm involved in. Before diving into details, let me just briefly share with you an overview of my CV. I am working for Eindhoven University of Technology in the Department of Mathematics since 2014. I, for myself, think that I develop mathematical models that accurately capture the data patterns, and I use them to make better decisions under uncertainty. I have been very lucky to be involved in several funded projects, including PrimaVera. And I'm also involved in the newly created 40U Resilience Center and the corresponding project there, Desire. So without any further ado, I dive directly into what will be the topic of today's presentation. So I was very much inspired by Marielle's slide on the roadmap. For me, it's not exactly a roadmap. For me, it's a treasure hunt. And I think that PrimaVera is in practice exactly this boat here, ready to embark in this huge trip. And my perception of this trip is that our goal is to discover a holistic approach for maintenance. So the way that I view things, please excuse me for just 1 second, I need to, yes, do that, and I'm back. For maintenance planning, and the initial idea is that we need to use real-time the data that we have. So as I said before, I have selected 3 projects. They are ongoing projects, and as such, the results, they vary. In part 1, where I talked about the maintenance planning for a single component giving a physical model, then this is, in some sense, the oldest project that I've been involved in, and as such, we have much more results. In part 2, I dive into a similar idea. Again, I'm treating a maintenance planning for a single component, but here there's a small twist. For this particular component, we don't have a physical model. Instead, we have a trove of data. And what we would like to do is indeed come up with the optimal cost planning for this particular single component view in isolation, given the data that we have. Then in part 3, which is my 3rd project, I would like to take all the ideas from part 2 and extend them now, not for the case of the single component, but for the case of a network of systems. All the systems are multi-component systems, and indeed we start again with a trove of data. So these are, in some sense, the highlights of this treasure hunting, but of course there are challenges in this trip. And some of the challenges that I will very briefly cover are the curse of dimensionality. The more realistic our model becomes and the more it can treat reality, then the problem is that it becomes quite difficult to handle in terms of the computational complexity and the computational time. What we also realize is that depending on the nature of the component, there are completely different types of assets, types of data collected, and as such, the corresponding models that we need to develop, they need to be tailored exactly to this particular type of the asset and to the particular type of data that we are collecting. So these are the 3 parts of my talk. Starting immediately with part 1, I would like also to thank my collaborators for this work, Colin Drent, Melvin Drent, and Joachim Arts, and show where the motivation comes from. So the motivation comes from a particular component of a complex system which is used for operations. And as you can see on the picture, here you have monitors. Patients lie on this bed, and what happens is that real time there is an X-ray video using a filament. And doctors use this information that they get from the monitors to navigate the operation in real time. So as such, the filament is one of the most crucial components for such a complex system. I'm going to view the filament as a component in isolation. And for this particular component, we have a physical model. This physical model was already developed by the company, and the question that we received is, how shall we do the planning? And the planning is based on a cost structure. So the objective in this context is to minimize the total cost for maintenance. So we have a population of components, and for that population of components, we have exactly the evolution of the condition of this component over time. We assume that failure, and this is also according to the company's practice, occurs the moment that this condition hits a predefined threshold. Those predefined thresholds are normalized values. What we realized by looking at the data of the company is, in practice, we don't have a single version of the component. What we have is a very heterogeneous population. If we are to see, and just a drift analysis, what is the drift by considering the first component, what is the drift by considering the second component, the third component, those are statistically different. When we try to cluster them into a population by considering geographic characteristics, environmental characteristics, some differences, mild differences in the design, we ended up almost having that each component is its own class. So as such, motivated by this statistical analysis, this is exactly what we do. We consider that each component is analyzed as a heterogeneous member of the population. We take into account the physical model that we have, but instead of viewing the physical model as the embarking point for the cost optimization, we consider the data to be the starting point, where we take into account properties that they come with the physical model. And that also has to do with the time domain for the failure. It takes a few years for a failure to exhibit itself, and we collect data on a daily basis. As such, there is enough time to learn the particular parameters of the model. So here I'm going to propose an integrated learning and optimization structure in order to reach cost-optimal maintenance decisions. While I go on with this presentation, motivated by the other speakers, I also have created questions, but in practice, I only have one single question for you. So my single question for you is the following. In those three parts, and I'm going to ask my question at the end of each part, I would like you to think if in your company you have a similar problem. Looking at the data, looking at the model, is there a case that we can use some of this work or extend this work for the purpose of your company? So I will repeat again the question at the end, and for now, let me go back to the presentation. So we have now all these different heterogeneous components that they bear the same structural similarities coming from the physical model, but with completely different parameters. And the idea behind it is that we would like to learn the model parameters as time progresses and make the decision tailored to the particular component and not the overall population of components. In a traditional setting, the way that we do this maintenance optimization, or the way that we solve this maintenance optimization problem is we bundle together all the components, then we, based on historical data, we estimate exactly what is the model parameters, and that would be an aggregated, for example, average. We plug this into our optimization problem, and then we end up with exactly this blue line here that indicates that we should do preventive maintenance before, at the moment that our condition crosses this point. So now the question is how to account for a heterogeneous population, extending exactly this very traditional framework of condition replacement policy. The idea behind it is to use Bayesian optimization. And the way that we do it is as follows. We maintain the structural properties of our condition over time, but what we assume is that we don't know the condition parameter, that theta, but we learn it in a Bayesian way. And every time we get a new level of condition information, so a new data point, then what we do is we update our prior with the observed data, resulting into a posterior, and that goes into a closed loop. that actually leads to our policy changing from a stationary deterministic policy to a policy that evolves over time. And in practice, what happens is that the evolution of the path determines exactly what should be the value of that threshold policy. To give you a concrete example, so you see here two realizations that are based on simulation. With a concrete line, what you see is the evolution of the data. The data is collected at every unit of time. The moment that this condition will reach our threshold equal to 10, then this is the point where it fails. And what you see with the dash line, and I play this on a loop, is exactly what is the policy. So to stop from playing and just look at the picture, then what happens is the following. In the left side picture, what you notice is that you have infrequent jumps in the condition, but those jumps, they are quite impactful. The size of the jump is quite large. On the right picture, what you see is a plethora of jumps, so you have multiple jumps, but they are frequent and small. And that has an effect on the policy. The left-hand side policy feels that the evolution of the condition is quite unpredictable. And as such, it lowers the threshold, the tolerance for preventive maintenance. The moment that we cross the threshold, this is the point where we do preventive maintenance. And if we have such a jump that it crosses over directly this preventive maintenance policy and the threshold for failure, then that indicates that we have missed our opportunities and we need to do corrective maintenance. While on the right-hand picture, what you see is because the jumps are, although more frequent but smaller in size, then the policy is much more tolerant and as such is higher. And in general, this is something that we can prove as a structural property. In case that you have few large jumps, then the threshold has a tendency to go downward, while if you have many small jumps, then the threshold has a tendency to go upward. And although this, in some sense, is the interest of a mathematician to be able to prove structural properties, it comes at a huge benefit. And the huge benefit is the fact that because of those structural properties, then we don't look for a general class of optimal policies, but we can guide the nature of the policy, and that minimizes computational complexity. So we can achieve in a rather complicated problem very quickly online results which are of true benefit. So typically the way that it would happen in practice and in the literature is that the unknown parameters are estimated by the historical data. And that policy is worse than the policy of simply updating our belief when it comes to the average, for example, of the parameters. And this is much worse in terms of cost than implementing a Bayes updating policy. To go back to my original example, this is the evolution of the data. And as I said, the data takes several years for the particular IXR component to develop a failure. So here you see a zoomed in, rescaled picture of only the last 40 or 20 days before the failure. And indeed, notice here that it has exactly the same structure that you've noticed in the simulation. So every moment in time that you have a new data, then there is a jump in the condition. The left-hand side has less frequent, in some sense, jumps than the right-hand side, but it has also larger jumps. And that results in the policy being less tolerable in some sense. We also estimated what is the benefit of implementing the different strategies. So if someone is to implement the historical strategy, that is our baseline versus just updating the parameters without taking into account Bayesian updating. And then the savings, they are in the range of 10 to 11%. If one is to implement the Bayesian approach that we are proposing, then you have a further benefit of 4 to 5%. So all in all, in this very simplistic one single component example, you can save 14 to 15% of costs for this particular component, which brings me to the end of part one. And at the end of part one, I would like to repeat my question. And I would like to ask all of you if in your company you have similar cases where you see this structure where you are interested in, based on a physical model, to compute what would be the cost of maintenance and what would be the optimal strategy for maintenance. So I feel a little bit lost trying to find where is the chat. So perhaps it's difficult to share the screen and also monitor the chat. Would it be possible, if you have such a case, to unmute your microphone?
Can I comment on that?
Hello?
Hello? Do you hear me?
Yes.
No, I think I hear. I was wondering, in your case, you have a way to continuously monitor the condition of your component.
I'm sorry, in my case I have?
You are able to monitor the condition of the component continuously.
Exactly. So in this particular situation, this is the case, yes.
And that is, I think, quite unique. Oh. Just a moment, I switch on my headset.
So somehow the connection is not very strong and I cannot hear.
Can you hear me now?
Yes, much better, Tito, yes.
Okay. My question, well, I observed that you have a way to directly monitor your condition, and that allows you to fit the model to your data quite easily. And that is, I think, quite a unique situation.
Indeed.
Which doesn't happen that often. So that might be the reason, to my opinion, that not many people have these kind of examples.
I fully agree. So this is my definition of a black swan. So,
yeah.
Or a unicorn. So it happens very, very rarely. And I know that for this particular company, it was an investment for several years due to the criticality of the component to come up exactly with this physical model. And indeed, that was also my guess, that very few companies would have such a possibility to invest time and also processing of data and also inputting sensors in order to be able to extract such a perfect condition of a system. So unless someone feels differently, then I think it makes perfect sense then to continue to part 2.
Maybe Stella.
Yes.
I'm not working in a company, but I remember from a project that we did at DAF many years ago, that they said because trucks are used in different environments, certain components follow different deterioration paths, and then dependent on the environment, for example, whether they transport concrete or other materials. You may not know where a truck is being used, but you can monitor the condition of the component. Yeah, and then I think you really have these multiple classes. That is your starting point.
Mm-hmm.
So then maybe your model is applicable.
Indeed, that's a very valid point. Yes. So I like very much this example. But
okay.
Yeah.
Yeah, I have nothing further to add, but I see the possibility to apply this maybe at more places.
But that also gives me the motivation to present part 2, because I also feel that indeed this is a black swan. This is a very unfrequently observed situation. In practice, what we see quite often is that we don't have a way to measure the condition. So what we have is data that could be in some sense revealing, perhaps not even directly, the condition of a particular component. And as such, still we would like to be able to do a few things. And that would be either give predictions about what is the remaining useful lifetime and with what probabilities we are in a particular, let's say, zone of times for the failure, and also be able to do maintenance planning. So this is joint work with a colleague from Eindhoven University of Technology, Jim Porteghis, and there's also a student involved, Bo Klasse. So in this project, what we are interested in is starting from the data to do exactly this notion of an integrated learning and optimization for the objective of cost-optimal maintenance planning. So here, as a motivational example, I'm going to look at bearings of wind turbines, for example. So according to the literature, like a bearing is very well measured through vibration. And of course, and that is also work that we have done with Alessandro Di Bucchianico, it's not alone enough to measure the vibration. But indeed, the vibration is a very good proxy for when a particular component is going to fail from the following perspective. A bearing, once it develops a crack, then what you see is that the vibration readings, they increase. So indeed, the higher the vibration readings, that is a justification to be concerned whether you should do preventive maintenance or lubrication of this particular component, or a list of actions that they are available to the disposal of the field service engineer. But if I think again about wind turbines, vibration data alone is not enough, in the sense that if there is a strong gust of wind, what would happen is that that will increase the vibrations. And not every gust of wind will break a bearing down. So we are collecting information which might reveal the condition of the underlying component. And what we would like to do is, given that data, be able to do the preventive maintenance planning of maintenance in general. So here a question of how to discover the condition and plan maintenance is addressed by also the work that Niels is doing and the work that Rob Basten is doing. So what we use here is an idea that comes from hidden Markov models. So in practice, what we do is we take the original data, and here you see just a simple illustration of how the data can be approximated by a condition. So we map the original data, in this case I only show the vibration data, into a condition of the system. And of course, this mapping is not going to be perfect, and the more information we have about ambient information, for example, temperature, what is the rotational speed of this particular bearing, or temperature at the bearing, or other sensory information, then the best this mapping will become. And every point in the vibration is mapped into a condition of our component. And here you see that the condition only has, here in practice there are 6 states, and those states are starting from perfect to good to fair to poor to imminent failure, and the last one is when it has failed. And the idea behind that is to use now the connection between the condition, but also the observations that we have, in order to be able to develop a maintenance plan. In a simplistic setting, we could say that as long as we have not crossed the poor or the imminent failure hidden state, then we do absolutely nothing. And the moment that we cross either the poor or the imminent failure, we do preventive maintenance. And if we cross, of course, the failed state, then we only have in our disposal corrective maintenance. So this is very much related to a presentation that Niels gave a few months ago in Eindhoven. And he explained there how to use hidden Markov models and partially observable MDPs. Here I'm going to have a small twist in that story, but I'm not going to go into many details of how to start with a collection of data. And the data doesn't need to be one-dimensional, it can be multidimensional, collecting, for example, data on the vibration, on ambient information, several variables, but what we need to have is those time series up until failure and including failure. So we need to have multiple failures captured from the installation of the component until the point of the failure. And here, depending on what is our objective, then we can, for example, the purpose of predictions, we can use hidden Markov models. We are assuming that the condition is not fully observable by what we see here from the data. And we have no way of influencing here no control over the state transitions. In some sense, the control is captured in the log files. So one additional source of data is the log files, in which case you also see they're captured. What happened? For example, what was the effect of lubrication? What was the effect of preventive maintenance? But this is in some sense beyond our control. And for the hidden Markov model, the underlying idea is that the condition of the system, which here is denoted with this S1, S2, and S3, corresponding exactly to these states that demonstrated before, going from perfect to imminent failure and the failed state, actually are the ones that they govern our observations. We do not observe what is happening on this level of this unobserved hidden part. What we only observe is the top part, which are the observations. We observe the vibration, we observe the ambient temperature, we observe the temperature of the component, we observe the information on the logs. All these things are observed. And we can use hidden Markov models in order to do predictions. We can also use partially observable MDPs. And that was also what Rob Baston is doing, and what also Niels mentioned in a talk of his. But here I would like to focus a little bit on mixed observational Markov decision processes. Mixed observational Markov decision processes are a generalization of the partially observable MDPs, in which case the decision is not only based on the belief on which state we are, but it is also based on the observation that we see. So if, for example, we still believe, and that is with 90% chance that we are in a first state, but our vibration readings are exceeding 2.12 G, which is the standard practice, and there is no wind, then that might be a very good indication that we need to intervene and have some preventive action, such as inspection of the asset or even a preventive replacement. So this type of mixed observational MDPs, they work in the same way as an MDP with the additional twist of the hidden part. So we start with our initial belief, and our initial belief is what are the chances that we are in any of those states. Then we choose an action. From our inventory of actions, we execute the action, we observe what is the output from that particular action, and then we update our belief given the action and the output. And that results in an updated belief, and the circle goes again, starts again. The only twist, as I said before, of this particular mixed observational MDP is that it accounts for what is the information also from the observation, not just the belief that one has on what is the hidden state of the condition of the component. So that was a particular situation in which I showed with data from vibration readings. They're a little bit too multidimensional to show more results on that, and we also don't have a baseline there to show what is the improvement of the cost yet. How we can use the data to actually predict the condition, in some sense create a health index for that particular component and do predictions, but also do decisions. So similar question as before. Would that be something that you see more potential to apply it in your company setting? Frigg, I see the question. You mentioned interesting. ISO continuous observables, can you also use warnings and messages? And the answer is yes. And actually, I'm going to demonstrate in the next part how to use the warnings and the messages. But perhaps you would like to unmute yourself and tell me a little bit more on the type of warnings and messages you have in mind.
Yeah, hi Stella. In our machine, we often have messages, and a lot of information is hidden in there. And we recently also did a study there if we can extract predictions of it for forecasting a part swap. We didn't use Bayesian techniques in there, but we used learning models to see if there is a correlation. And for one example, we found one, but it is very interesting to see if you can use the power of the Bayesian techniques in which you have the initial assumptions, the expert knowledge about the probabilities, and feed them with the data.
So the idea behind this hidden Markov models is that indeed you start with any relevant data that you have, and you try to build what would be a proxy for the condition. And one choice that you can make beforehand is how many levels, how many states you would like this proxy for the condition to have. Mm-hmm. That is about predictions, and you can use that for a prediction setting. And the other thing is that in addition to the prediction, it gives you also a certain belief in where are you in terms of the particular states of the condition. Like, what are the chances that you are in a perfect state? What are the chances that you are in a good, in a poor state, and so on and so forth. And you can use that as an input to make decisions.
Okay, interesting. Let's.
I think it's
offline,
worth.
We have to talk about it.
To pick it up, yes.
Yeah.
Someone else would like to contribute?
Yeah, I think, Stella, so warnings is something that comes back at multiple companies. What I notice is that in the research, there's a whole stream of literature where we now use partially observable MDPs or related things to include these indirect observations that say something about the degradation state. But I sometimes also miss a sharp overview for what are the different types and what are the really different structures that are assumed and what are the appropriate techniques to use. And I see a growing field there, but also as a researcher, I sometimes miss the sharp picture of what needs to be done when exactly. I don't know, do you have such a sharp overview?
To an extent, yes. So what I love about hidden Markov models is that they make an assumption that the underlying hidden condition, let's call it, it's a Markov chain. So we don't know in practice if that is true. We don't know exactly how realistic of an assumption this is, since we cannot observe this Markov chain. Then it makes almost zero assumption on what would be the observable aspects. So what would be the structure of the data that we feed the model. Depending on how good of a structure you have, then you can go very far with exact analysis. If you don't have a good structure, so you can do numerical analysis. And with Jean Porteous and with Paul Klasse, what we are currently developing is a tool, and actually our objective is to make the code publicly available. It's written in Python, that you just feed the data and then you get the condition and you get the decision, but it's going to be a simple decision, just do preventive maintenance, do nothing, or do corrective maintenance. And you can fine-tune the cost for that. And we would like to try it out with some more cases that come from companies and see how well it performs in practice. So that's why I find it quite important. If the companies do have this type of data, then it would be wonderful to test it there and see what would be the results.
Yeah, I think, yes, go ahead.
I agree with Stella. I also see hidden Markov models and POMDPs, etc., as a very viable model to use for predictive maintenance. And I use them a lot. Also, Niels uses them a lot, and yeah, I think it's a good decision model.
I agree, but I think that. Also, companies could be helped by guiding in what technique can fit for which data structure, for which basic assumptions.
That's truly the case, yes.
So that is maybe something that we can work on as a team.
Mm-hmm.
Okay, then I would like to move on to part 3, and we will make it perfectly on time. So in part 3, what we have done, and here you will see many names appearing, Paulo da Costa, Peter Verlijnsdonk, Simon Forberg, and Willem van Jaarsveld. This is a group from TUE. We are all working together from within an NWO proposal, and our objective is to develop a maintenance planning holistic approach for a network of systems given a trove of data. And the idea here, and I'm going to present, because this is very much into the genesis, a very simplistic toy model. We have a field service engineer, and you see actually the field service engineer is this blood dot that moves into our network. And the grid here that you see is the network. We have a strategic location that could be, for example, the supply chain headquarters. Then we also have machines. These are multi-component machines that they are depicted here in blue. We have 4 of them, and those machines, they produce alerts. When they produce an alert, they give the following information: the timestamp at which the alert was produced, what is the time, minimum time for the failure, then the next component is maximum time of the failure, and what is the probability that we are exactly within this time domain. And we can use actually the hidden Markov model to produce exactly this. In particular, I think this was produced by support vector machines. So the decision maker here only observes these alerts. And what we would like to create is a maintenance planning using all this information real time of how the field service engineer is going to select which machine they're going to maintain, in which order. And of course, it could happen that a machine fails. If a machine fails, then you see it depicted here in red. And there, a corrective maintenance needs to take place. So for this particular model that you see, there are several challenges, because this particular model incorporates a travel salesman problem. The field service engineer moves into our network. We have a real-time scheduling problem. We have a maintenance optimization problem where we have only assumed that we have preventive, corrective, do nothing also actions. We have a downtime cost, and we have some level of information that comes from these alerts, which is a hidden version of what is the degradation, what is the condition of these components. So we have a partial information environment, and in practice we don't have just one field service engineer. That is our toy example here, just to demonstrate what is happening, but we have a multi-agent problem. So these are the challenges that we would like to bring together and solve this problem. And in some instances, we have actually solved this problem. So if the problem is very small, so for very small scale problems, we have actually exact methods and underlying MDP that we can solve it. We also have implemented a learning method based on deep reinforcement learning, where we simulate many episodes and then we learn the policy. And we have also some heuristics which are based on some simplistic ideas that one could implement in terms of the policy. So the field service engineer just visits the nearest neighbor when there is an alert or a failure, or greedy based on the distance, the cost, and the time, or a deterministic problem by first-order approximation. And we use these heuristics as a baseline to see how far we are from the deep reinforcement learning. And I will avoid going into details. I will put the slides online so you can see more information there. So training with a deep learning idea reduces the average cost of the problem, and this is a value that I will come back in the next slide, that's why I'm mentioning it, to a total cost of 3,232. So this is what we try to beat with our heuristic approaches. And with the heuristic approaches, for example, the nearest neighbor has an average cost of 3,800 for values that we chose, and here they're a toy model, simplistic values. But we also notice that 3,800 is not that far in terms of the policy. And this has to do with a particular structure, with a particular properties of this network. So we assume here that every machine is 1 unit of distance away, and it takes exactly 1 unit of time to repair preventively or correctively a machine. As such, the nearest neighbor is a very greedy way of a greedy policy that could be implemented. The next step, and that is for future research, what we're planning to do is actually solve small instances exactly and come up with policies that they could actually capture more elements of the problem and then try to compete against the reinforcement learning algorithm. The reason why we would like to compete against the reinforcement learning algorithm is not that we don't trust it or it doesn't have wonderful results, is because we would like to gain some insight on what is happening and what are the factors and how do you balance the cost, the distance, how do you make these decisions, rule of thumb, in a rule of thumb sort of way. Because what we have also seen is that field service engineers, sometimes they don't trust the outcome that comes from a machine that says, you need to do that. Their intuition on the matter might be completely different, and as such, they might question. But if we have simplistic rules that would give us not so much different cost, then that would be quite easy to implement. So as a last question, would this particular setting, and I know that I just presented it very quickly and in a toy model fashion, would that be something that you see potential of implementing in your company? Okay, so let me test if the connection is working. So now I'm worried, can you hear me?
Yeah, we can hear you.
Okay, fantastic, because I was not getting an answer, and that's always a concern with online meetings.
Mm-hmm.
So, Tito, since you were the one that reacted to the question, then may I pick your brain on, given your experience in the area and this field, do you see a potential for this particular type of models?
Yeah, I mean, I think this is a situation that quite some companies are in, and if you can somehow optimize that whole process and find the solution with the lowest cost, I think that would be a good solution for a lot of companies. The challenge always is to have the right input. So assuming that the machine gives an alert in time, makes it easy to, well, not easy, but allows you to do these kind of optimizations. But the challenge then in practice is always how can you reach the state that the machine gives that alert in time, and how accurate is that alert? But still, I mean, assuming that will be possible in the future, I think all the steps behind in optimizing this whole problem are quite interesting.
But I think that this is also what makes our consortium extremely unique, because we do cover the entire chain, from the development of sensors to the installation, to the analysis of the data, to the maintenance planning, to the holistic approach around it. So from that perspective, I am hopeful that within our consortium, we may be able to achieve this.
Yeah, I fully agree. I think the nice opportunity is now to connect all these approaches. And indeed, if everybody solves his own problem, then in the end we have a very nice combination of all these approaches. So that should be the final goal, I think.
And I think even the problem without this traveling salesman problem embedded is already interesting, where you just have multiple versions or multiple items in a fleet, and then you optimize the planning is already interesting. So a little bit simpler version is also very relevant.
That's a very good point, Mariella. Yes, because it's quite easy for us to also adjust for that. Eliminate the time constraint of the field service engineer for traveling, for example, and only look at what would be the ranking, the listing of the maintenance problems. When should we do maintenance? So that brings me to the conclusion of this presentation. And now I think I would like to give the floor to you if you have any other questions.
And maybe to challenge you further, Stella.
Yes.
Suppose you're able to combine your models for a whole system. Then there's a lot of data that is collected, a lot of warnings. What do you then see as the approach for systems as a whole? And think also of systems consisting of 100 or more critical components for which you know these degradation processes and receive imprecise information.
Yeah, so that is a very interesting question, Hertjan. One of the challenges that I see is that depending on the criticality of the component, depending on the time scale of how long does it take a certain failure to exhibit on the nature of the data, then the underlying methods that we foresee might be completely different. And I think that is the biggest obstacle, in some sense, hurdle in developing a holistic approach that could fit everything. So I think that the first step towards the future is indeed like understanding the particular needs of the data and making an inventory. For example, saying that if the nature of the data is like this and you have this level of information, this is the logs, this is the data that you have, then this is a good way to move forward, and then make this inventory and then create a holistic approach exactly based on these aspects.
Hi Stella, Freek here.
Hey,
question, your story about maintenance planning and the three parts of it. I have a question about how good can this be adapted to the situation of a new product introduction? In the learning phase, what's really the quality of my product in the field in the first year? Your Bayesian adaptive methodology is maybe a good strategy in that entrance phase.
So that is an excellent question, and something that has troubled me quite a lot, in the sense that most of the approaches that we currently have in our disposal, they do assume that we have multiple failures. We have time series from the installation of the component until the failure. And indeed, if you have some idea of a structure, of an underlying physical model, as it was part one, for example, and then one question is, because there were some changes in the design or because there was a new, relatively different but still bearing similarities component, you can use that structure and use the Bayesian learning to just fine-tune the parameters of that physical model. But you need to have a certain level of knowledge, either enough data so then you can create a model, or some notion of a structure for the model and then use the Bayesian in order to learn real-time the model.
You can, for instance, use the patterns in the prior machines or product you had, and use that as the starting hypothesis is for the next products.
Exactly.
Thank you.
Are there any more questions? If not, then I would like to thank you all for attending the talk today. It has been my pleasure seeing you online, and I'm hoping to see you again in the new version of the colloquium after the holidays. Enjoy the summer and see you all very soon.
Okay, thanks.
Thanks. Bye.
All right.